Okay, actually my constants here were spot on. Well, except this was 6.38. So let's go ahead and just put this in on the calculator. Be fun. There we go. We've got, oh, I've got to hurry this along a little bit. All right, so here we go. So we've got, so the force, we're going to use this formula up here. So it's 6.637, 6.66, oh, I know you all hate it when I do that. 6.673, 6.673. There we go. I get 6.37 to 6.673, second E, oops, to negative 11, times the mass of the Earth, which was 5.98, second E to the 24. Gosh dang it. I meant to turn that off. And then times the mass of the man, 100, divided by, double parentheses, I'm going to go with their 6.38, second E to the 6th squared. What was that? Boom, 980 kilograms. So the force that 100-gram man feels is 980 kilograms, or 980 newtons. 980 newtons. I wonder what his acceleration is. So we take the force over the 100 kilograms, take that 980 newtons divided by 100 kilograms. I get 9.8 meters per second squared. I'll be a monkey's uncle. That must be where that comes from. You're right. And if we didn't have friction, the other cool part, if all of a sudden some evil person took away all the frictional forces, everybody would be hanging down around the equator. We'd all be sliding because the gravitational field up here is less because the radius is smaller up at the top. So we'd all slowly slide and be hanging out at the equator, trying to fall through the center of the Earth as it's spinning really fast. Okay, well that was fun. So here they just take two particles and put them next to each other. 6.673 times 10 to the negative 11. All right, Earth and Moon. I think they might go ahead and add in the radius here. Oh, we've already done this. Why am I going backwards? Oh, I've put that in. I'm sorry. Here we go. There's only one speed that a satellite can have if the satellite is to remain in an orbit with a fixed radius. Okay? In other words, it wants to stay there's only one speed that a satellite can have. Okay? And here's what we do. This is really cool. If it wants to stay at a fixed radius. All right, so here's what we do. We go, okay, what's the speed of the satellite? Whoops, wrong thing. All right, so we've got this. We've got the satellite going around the Earth, a fixed distance from the Earth, r times, where this is r, where we're going to have to add the radius of the Earth also to the height here. So r is equal to the radius of the Earth plus the height of the satellite. Okay? Now, he's going to go at a, what radius is going to keep him at that same speed? Okay? Got to find v. Well, if he's going around the Earth, he feels the centripetal force going inward. And that centripetal force is going to equal the gravitational force that he feels at that height. All right? It's going to equal the gravitational force that he feels at that height. So we have this. We've got centripetal force, which we learned was mv squared. This is the mv of the satellite over r is equal to g, mass of the Earth, mass of the satellite, over r squared, where again r is equal to re plus h. This is all cool. I love this stuff. Okay. Well, what cancels right away? The m's. What else cancels right away? One of the r's. In other words, if I divide both sides by m, I multiply both sides by r. So here's what I did. I multiplied by r over m, r over m. That's what happened. So I get v squared is equal to the square gm, mass of the Earth, over r. So then v is equal to the square root of gme over r, where r is re plus h. So what does this tell us? What does this tell us? Here's one of the interesting things about this. This tells us that what happens as r get bigger? As r gets bigger, what happens to v? R increases, the velocity decreases. Okay, so the higher the altitude I send something, the slower its speed is going around the Earth, and the longer its period is going to be too. In fact, here's the big idea behind this. Here's what we use this for. So, GPS satellites. They need to stay in one spot above the Earth. They need to stay in one spot. And there's a whole bunch of them lined up at a certain radius above the Earth, height, altitude above the Earth. A whole bunch of them lined up that are staying in one place. They are called geosynchronous. Weather satellites are the same thing. Geosynchronous satellites. Geosynchronous, meaning their period T is equal to 24 hours. They're staying in the same spot above the Earth as it goes around. Okay? And since their radius is higher, their speed is smaller than that of a big radius. So they got a big radius of orbit. Spy satellite. It's got to go fast. Oh, another satellite is your dish TV, if you have dish TV. It's got to stay in the same place. So we can bounce signals off of it. We know where it is. Okay? And your dish shoots out into space. You know, if it was always moving, you think you got crappy service now. Spy satellite. Small radius. Much closer to the Earth. Takes pictures, moving fast. Okay? It's down there moving fast. So let's take a look at what is the period? What is the speed of a moving slow? So this one's moving slow. What is the speed of a geosynchronous satellite? In other words, it stays geo, it stays in the same place above the Earth, and it's synchronous, it's got the same period. It's turning with the Earth. It's keeping a speed so that it's turning with it. What is that speed? Okay? That gets to be tricky, and we'll do that in the next one. I want to make sure I practice it. I just don't want to jump into it, because that could be ugly. Cost thousands of lives. But we'll look at it because it's one of your homework type problems. It's like that.